So this is 9.4 in the textbook. Homework assignment going through projectiles and quadratics. So question number 1, in your own words, define the term projectile. So let's stop there. I'm going to define a projectile as something shot or dropped or thrown, and this is the most important part, through the air. So something is going to be in the air affected by gravity. If it had an initial velocity, it could go up, but eventually it will come down because of gravity. So we want to say through the air. Something dropped in water, for instance, is going to fall at a different rate than something that just dropped through the air. So we do want to be specific there. Give several real life examples. I'm going to say cannonball shot out of a cannon. A rock dropped off a cliff. A baseball thrown in the air. Okay, all could be determined to be projectiles in terms of studying the gravitational pull on it, how long it takes before it peaks, if it was initially thrown up, how long it takes to come down, and being able to find the different heights along the way. So we are going to question number 3. We're going to do parts A and B. So we have a ball being thrown from an initial height of 5 feet. Now that's important because you might think, well, why do we have to say it's from 5 feet? It's the person standing on the ground, so wouldn't it be 0? But they're going to let go of that ball above the ground. So let's say they're about 5 feet tall, or maybe they're a little shorter than that, but their hand extends up. And so when they let go of the ball, it's exactly 5 feet above the ground. We need to include that there. Okay, if a ball was hit off the ground, like say a golf ball, then that would have an initial height of 0 because it was off the ground. Otherwise, if we don't add that in, then the initial height we're going to call 0 basically, and then the ball could fall below that height because if they let it go above their head, the ball could eventually fall lower than that. And we would have negative numbers at that point representing the height of something. And so ideally, if something can drop all the way to the ground, we want the ground to be 0, so the initial height here is 5. All right, and it's being thrown up, so it has an initial velocity of 30 feet per second. Gravity will pull on that and slow it down until eventually it stops and starts coming back down. So we have 2 equations. One is in feet and one is in meters. They're actually the same equation. We just convert feet into meters. And so this is in feet, which then the equation reads negative 16 t squared plus, I'm going to go ahead and write it up here, the actual formula, negative 16 t squared plus the initial velocity, which is v with the subscript 0, times time, plus the initial height. In the book, instead of using h again, because that can be confusing, they used the s. Okay, but I like to use little subscript 0 for initial height. And so when we plug in here, our initial velocity was 30 times t. We don't have time. Time's going to be different all along the way here. And our initial height we just talked about was 5. Okay, so part B, we're going to go ahead and plug in a number. How high will the ball be 2 seconds after it's thrown? So that's time. We want to find the height. So h stays. We plug in for time. And you can plug this all in your calculator, or you can go one step at a time. 2 squared is 4, and 4 times negative 16. You might say, well, I don't know what 4 times 16 is. I know 2 times 16 is 32. So 4 times 16 is going to be 2 of those. So it's negative 64 plus 60 plus 5. Going left to right, that's negative 4 plus 5, and that gets me 1. So this will be 1 foot off the ground. 1 foot off the ground. So it's actually lower at this point than it was when it was initially released at 5 feet. Okay, so 1 foot off the ground. And like I said, if we didn't call this 5 and we called it 0 where it started, now it's actually lower than that. So we'd have to express the height as a negative number, which really doesn't really make sense in this situation. So we had to call the ground 0, so the initial height was 5. And so now it produces a 1. We know it's 1 foot above the ground. All right, number 4 now is going to talk about meters. And so it's the same exact formula. I'm going to have something in front of t squared plus initial velocity times time plus initial height. But instead of negative 16, which is the gravitational pull in feet, that's what it represents, this is negative 4.9 in meters. So plugging in, we're just doing part A. Let's see what they give us. They give us initial velocity of 26, and they give us initial height of 1 meter. So h equals negative 4.9. That comes from the fact that it's in meters. Initial velocity goes here, 26t, and the initial height goes here, so 1. Now the reason I cut out some of these questions, the extras, the B's, the C's, is because in order to do these, you're going to need a graphing calculator, and currently with all of us not being physically in school and not having graphing calculators, some of you I know were able to download the calculator on your computer. Scientific calculator on your phone is not going to be enough. You need a graphing calculator to solve a lot of this stuff. So we cut them out. But just know that we could find the maximum height on number 3. Using the graphing calculator, we could estimate when the ball is 5 meters high using the graphing calculator. Okay, but that's why we skip those, is because of not everybody's going to have a graphing calculator during this time. All right, we're on to number 5. 5, we are going to do A, B, and C. All right, an object is dropped from an initial height of 40 feet. So what is its initial velocity? It's dropped. So what's the initial velocity? So if it's shot out, it comes out at a certain speed. If you threw the ball, right, then it's going to have a certain speed. But since it's dropped, how fast is it moving when it starts? That is going to be 0. So initial velocity equals 0. Because when this starts, it's not moving. So velocity is how fast something is traveling. So the initial velocity is 0. What's the maximum height? So it's dropped. So the point when it's first let go, that's going to be the maximum height. It's going to fall from there. And so 40 is going to be your maximum height. So part B, if all this is true, let's plug in. We are talking about feet. We're going to write a formula. So h equals its feet, so negative 16t squared. Now, if I was going to write the whole thing out, including the 0 being plugged in, it's going to go in for initial velocity. So 0 times t, well, 0 times anything is just going to eliminate. So this is going to go away. Our initial height was 40. So this fully simplified with this out of here now. H equals negative 16t squared. We don't need this middle piece, plus 40. So when you see one of these equations, that means it didn't have an initial velocity if you don't have that middle t in there. Okay, meaning it was dropped. All right, so that was part B. Part C. After how many seconds does the object hit the ground? So t represents the time. We're going to solve for time. They're asking how many seconds. We have to find it. In order for us to solve this, we need to plug in for one of these two. So since we're solving for time, that means we're given height. But I don't see a number, so we have to think about it. After how many seconds does the object hit the ground? What's the number that represents the ground? That's 0. So it starts up at 40, and it's going to drop, 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 drop. Over time, we're going to go down from 40 until we eventually hit the height of 0. So if we want to know about what time this hits the ground, we're going to have to put in 0 for the height, and we're going to solve this equation for t. So this represents when the ball hits the ground, or the object hits the ground. So I got to solve this. This is from previous sections now. So minus 40 from both sides. Got to try and get t by itself if I want to solve for it. So I have negative 40. I'm going to divide by negative 16. So I'll get a positive. I'm going to have t squared. I'm going to bring this up here just to save room. I have t squared left over on the right side of the equation. And now I need to do some division. 40 divided by 16. It's 2.5. Yes, they're both negative. They will cancel, make a positive. And that is not the final answer here. It is not 2.5 seconds. I have to square root this to get t by itself. So I'm going to square root 2.5. And it doesn't tell you how to round or anything like that. In just everyday language, they're saying how many seconds. So we're not going to list out all of these numbers to say it was that many seconds. So about 1.5 seconds, but that 8 would kind of round it up. So I'm going to say about 1.6. About 1.6 seconds. About 1.5. Okay, we're rounding it off. It's not going to be a perfect number. Okay. Number 6. All right. So the object is dropped again from a height of 150 meters. So when we have this equation, first thing we're going to do, we're going to write the equation part A. It is in meters. So h equals negative 4.9 t squared. Start there. And we're going to have to plug in for initial velocity. So since it's dropped, there is no initial velocity. So we're not going to have that middle piece. It's 0 and it clears it out just like we saw in number 5. And the initial height is plus 150. Okay, so part B. After how many seconds does the object hit the ground? Same question we just solved over here. So we're going to plug in 0 for the height. We want to know when is the height 0. It starts at 150. It's dropped. So you can see this is a negative, and as time goes up, it's going to create a quote-unquote larger negative number, even though it's not larger, it's actually smaller. But you're going to get 4 times this, right, is going to be negative 16 plus all the decimals. But if you put 10 in here, 10 times this can be like negative 40, so on and so forth. So that number is going to be negative, taking away from the initial height of 150. So we want to understand this equation. This part is bringing us down from 150. We're dropping it from 150. So the second we drop it, it starts getting lower and lower and lower until eventually it hits 0 on the ground. So we want to now calculate about what t is. So we're going to try and isolate t, just like we did up here on number 5. Clearing this out, so negative 150 equals. We're going to divide. And I don't expect this to come out to a perfect nice number. So again, 2 negatives will cancel. 150 divided by 4.9. I'm going to write all that down. I don't want to round it because I still have work to do. So what I need to do is take the square root of that number. So if I shortened it and take the square root, I'm going to get a different answer than if I take the square root of the whole thing. Now, if you have a graphing calculator, scientific calculator, there's easy ways to grab this number, or you just retype it. But I'm taking the square root of. If you can, you just go highlight your last answer and hit enter, and it brings it down for you. Quick and easy. So taking the square root of that number, so t equals about 5.5 seconds. All right, so we are moving on to number 9, C and E, and 11 through 14. Okay, Number 9, a small rocket is shot from the edge of a cliff. Suppose that after x seconds, the rocket is y meters above the cliff, and here's the equation that represents that. So notice x is in the t spot for seconds, y is the meters above the cliff, that is the height. And so we are just doing letters C and E. So letter C, how far above the edge of the cliff is the rocket after 4 seconds? They're giving you time, so we're going to plug directly in for x, because that represents the time in seconds. So they said 4 seconds. Oops. And you can see they kind of wrote this differently, right? They put the squared piece second. It's okay. Just be careful, don't put the squared here just because we're used to it in that order. It doesn't have to be given to you like that. And so we just need to solve this out. Let's see. Technically, you want to do exponents first, right? So this is going to be 4 squared, 16 times 5. And over here, we're going to have 25 times 4. So we're going to do our multiplication next. So we're going to get 100. And then 5 times 16 is 80. So y equals 20. And you can see they used -5 here. -5. So they rounded that meters up from 4.9 to 5. So they just wanted to make sure we're all using the same formula. So it looks like this. And we're going to letter E. What is the height of the rocket after 6 seconds? So let's see what happens when we plug in a 6 now. So again, 6 squared, first thing you want to do, get rid of your exponents. So we're going to do 5 times 36. That's 180, and 25 times 6 is 150. And so we want to look at this, and we're going to get -30. But remember, this was shot off of a cliff. So our answer here is just -30 meters. But what does that mean? That is 30 meters below, not the ground, because we're up on a cliff. I guess the ground of the cliff, sure. But if it goes down past the initial height, it could still be in the air. So it's 30 meters below the edge of the cliff. So that's what the negative represents there, that it's below the initial height. Because it was shot off the side of a cliff, that obviously can happen. So we want to make sure we understand the negative. It's not incorrect. It's not below ground because it was the cliff. Okay, so understanding that negative there is important. Going to number 11. So now some review, but still looking at these parabolas. Part A and B. A, we're going to make a table from -3 to 3. All right, for the equation y equals 1/4 x squared. So when I plug in -3, -3 squared is 9. We're going to do 9 times 1/4. Timesing by 1/4 is the same as dividing by 4. So it's actually 9 divided by 4. 9 times 1/4. And these two numbers are going to be equal, obviously, right? 9 divided by 4, 9 over 4, 2.25. We should also know that 1/4 is 0.25. So you could have done 9 times 0.25. And again, you get the same answer. So we've got 2.25 here. When I plug in -2, squared is 4. Divided by 4 is 1. Plug in -1, squared is 1. Divided by 4 is 1/4, or 0.25. Again, you can run this through the calculator if you need to. Plugging in 0, you square it, you multiply, it's still 0. 1 goes in, it's going to behave the same as -1 because we're going to square it. So when we square -1, we get the same answer as when we square +1. So 1 squared is 1. A fourth of 1 is 1/4, which is 0.25. 2 squared is 4. A fourth of 4 is 1. 3 squared is 9. A fourth of 9, we already calculated, is 2.25. So there is our table. Quick graph. -3, +3 for my x's. My y's, I can also go to 3 because I only have to get to positive 2.5 from 0. Okay, so not that far to go here. So I'm going to start in the middle. Since that's my vertex, I can see that it's going to be the same, symmetric on both sides. So here's 0, 0. At 1 and -1, it's at 0.25. So if I'm counting by ones, 0.25 is not even half. So here at -1, same height at +1. When I get to 2 and -2, I've made it to 1. 3 and -3, I am at 2.25, so a little bit above the 2. And then, of course, that will start to climb steeper and steeper. Okay, number 12. Also making an XY chart. Same process from -3 to 3. Except now we're going off this equation. So we're plugging in -3, running the numbers there. So let's try plugging this one completely in and see if we can get the right answer. So 8 times -3 minus 3 times, now this is important, we've talked about when you're plugging a negative in that's being squared, you need parentheses. So the -3 is in parentheses, we're going to square it, and the parentheses tell us that the whole thing, the -3, is being squared. If we don't put the parentheses, it's only going to square the 3, and it's going to leave the negative out front with the number. And we know anything squared, if it's negative, becomes a positive. So if we don't put those, it's going to leave the negative out front and give us a negative answer, which is going to mess all of this up. So we really got to be careful when you're plugging this all in the calculator and make sure that you've got it all with parentheses correct. So -51. Plug in -2. So 8 times -2. If you want to put that one in parentheses, that's fine. You don't have to. Minus 3 times this one I do need to put in parentheses because it's being squared. So I get -28. -1. Put it in parentheses. And when I take a look at my answer key here, something seems off. What did I do wrong? Oh, it's a minus. Okay. So I put a plus right there. 8 times -1 minus 3 times -1 squared. There we go. That's why it's good to work with an answer key. Some students are afraid to do that. They feel like it's cheating. But if you're doing the work and then constantly checking the answer key as you're going, you catch your mistakes right away. If I went all the way through this whole thing and then look back, I might not even remember what I was doing. I might have cleared my calculator at that point and had no idea what I messed up. And so it's helpful to just keep that answer key handy up on your computer, your phone, hard copy, and check it as you're going so that you can catch your mistakes immediately. And it's much easier to understand your mistakes, which is the most important part of math really, is understanding the mistakes you're making, fixing them, and when you understand them, you're very much less likely to make them again in the future. If all you know is you made a mistake, you don't know what it was, what happened, and then you just fix it, you just change the number, well, chances are you're probably going to make that mistake again in the future because you haven't corrected it. So again, having that answer key close, you can see how I just benefited from that. Not a bad thing. Plugging in 0, if you notice, 0 squared times something is still 0. 0 times 8 is going to be 0. It's going to be 0 minus 0. So we are going to have that 0.00 here. What about 1? Now you might say, well, 1 and -1 should be the same, but that's not true in this equation because they're going to be squared here. We're going to end up with the same number on this term, but 8 times 1 and 8 times -1 will give us different numbers here. So even if this number is the same, we're going to be starting with either a negative version or a positive version of 8 minus something. So they will produce different numbers. So 8 times 1, which technically you don't have to write that, minus 3 times. Now I don't need the parentheses anymore because it's not a negative number. Wouldn't be wrong if you put it. It's 5. 8 times 2 minus 3 times 2 squared. It's 4. And 8 times 3 minus 3 times 3 squared. It's -3. So just taking a look here, I don't necessarily see a vertex, right? I don't see numbers that are equal on both sides of a vertex. So we're going to go ahead and graph this. And it's curious to see what is this going to look like. Clearly, it was in the negatives, getting closer to 0, gets past 0, right? It goes all the way up to 5, and then it starts going down. But 5 is definitely not the peak. If 5 was the exact peak, the highest point, then that would be the vertex, and you would see equal numbers on both sides. So that's not our vertex. We got something else going on here. So -3, +3. I got to go all the way up to, or down to -51. So I'm going to count by tens. 10, 20, 30, 40, 50. Same thing up top. 10, 20, 30, 40, 50. Even though I'm not going to go anywhere close to that. So at -3, I'm all the way down at -51. At -2, I'm at -28. At -1, I'm at -11. I hit 0, 0. 1, I'm at 5. 2, I'm close to that. I'm at 4, so I mean barely below it. And so as I went from here to here, it was still climbing, right? These two, hardly any difference. So it's not going to be flat, but that's going to be where my vertex is right there. Just past that one that was at 5. And then 3, -3, I'm going to be starting to go back down here. So as I connect these, you can see I'm climbing, and the peak is going to be in here somewhere, and then it starts going back down. So the information wasn't given to you perfectly there with the vertex. It's not always going to be cookie cutter like that. And so our vertex could be between two of these whole number points because the vertex can be at an x value that's a decimal. All right, we just have 13 and 14. So 13, we're looking at the graph, 14 as well. We're going to use symmetry, so knowing that on both sides of my vertex, there's going to be some symmetry here to the numbers. Find the coordinates of point A and B. Okay, now you could just count, right? But what we need to know is that there is a line of symmetry called the axis of symmetry, which we're going to solve for in 14. What's the equation? It's the line that cuts this in half, and that means that it's symmetrical on both sides. They're going to be the same distance away. So if I've got this line cutting this in half, 0.55 is 1 to the right, and so point B is 1 to the left. So 1 to the left of here, if you look at your x values, here's 4 and 5. So 1 to the left would be 3. I'm actually going to start with point B. My x value is, oops, not 5, 3. So here's 5, here's 4, it's 3. And my height, this height was 6, this height was 5, so this height is also 5. Now you can just count boxes, right? 1, 2, 3, 1, 2, 3, 4, 5. So it's 3, 5. So because it's given to you on a grid, it's kind of, to me, too easy because you can just count boxes. But if this was given to you not on a grid, you could still figure this out without just counting boxes, because you could have your line of symmetry and you know that this was 1 down, 1 to the right. So this is going to be 1 down, 1 to the left, and you could manipulate those numbers if you had to. And so letter A, you can see it's 2, 2. But what you could also notice is that this point on the other side of the axis of symmetry, from the 6, it went down to a 2. So this is also going to go down to a 2. From the 4, it went up to a 6, counting to the right. So we'd go down 2 from 4 to the left. And that's where the 2 comes from. All right, number 14, last one. What is the equation of the axis of symmetry? So the axis of symmetry, again, is this line that cuts this into two symmetrical halves. And so axis of symmetry for parabolas that are upright like this, whether they're upside down or they're pointing upwards, the axis of symmetry will run up and down and always have the same x value. So the x is always going to equal 4. So x equals 4. No matter where I go on this line, the x value is 4. And that's the equation of those types of lines.